I'm gonna hand it off to sorry, Isha. I'm gonna hand it off to Isha to do a little bit of the overview of the sensors. We went through slightly some of them in the beginning, but just repeat them and some of the description of the sensors.
Okay, yeah. Let me just share my screen. So here again is sensors. So just to go over, this is a camera, and camera works with vision-based tasks and can be combined with Vuforia and TensorFlow. So the camera helps, when combined with the Vuforia and TensorFlow, it takes what's seen and the Vuforia can convert it in differentiate pictures. And then here's a distance sensor, and this is used for localization. And localization is finding your location relative to something. And what we're talking about is the board, or I mean like the mat, or like the whole what's the word? The FTC like game. So that's where you're trying to find your location relative to like objects or the walls or certain things. And then we have the color sensor. So this is an alternative to a camera, and this works with color related tasks. So if there's like a blue field line or a red field line, because you could be assigned to like the red team or blue team, this helps you like differentiate which colors you're trying to go to. So that's another overview of sensors.
Yeah, I'm gonna go into the a little bit of the explanation of how to use these sensors, starting with the distance sensor, the color sensor. Those are two of the simpler sensors, and then I'll explain. It's not in this presentation, but I'll explain the gyro sensor, and then the color sensor. The webcam isn't a direct like sensor, but programmatically, but it is used in Vuforia and TensorFlow. Okay. So similar to how the DC motors are knitted, everything inside FTC, like all the sensors, all the motors, are contained within the hardware map. So this time, instead of a DC motor, for example, you can say color sensor. And again, this depends on what it is in your config, but whatever you have it named. So if it's called color sensor, you would just use the name of whatever it's called in the config. If you don't type it in correctly, it'll say error, like color sensor not found in config. So this is a very simple code that initializes a color sensor. And there's various types of color sensors too, but all of them contain similar code on how to use them. Actually, let me start even simpler with the, or I can go into this color sensor. So to log the actual, just directly log the value of the color sensor, you can just do color sensor.get. Color sensor, there's three variables, red, green, and blue. So like most RGB systems, the color sensor tells you how much red, how much green, and how much blue is in whatever it's sensing. So we found this in previous years, and this year, one of the use cases is to, like, for example, detect the red or blue tapes on the ground. Depending on where you are, for example, you might determine that you want to stop moving or start moving based on where the tape is. So if you want your robot, here's a very simple example. If you want the robot to keep, I'm going to write this in the style of in autonomous. What we could do is we could read the value of the red tape. So it's returned as an int, and I believe it's returned between 0 and 225. You have to you want to read the range. So you might want to like manually put the color sensor over the red tape. And let's say when the color sensor isn't on the tape, the value is like right around 0. But when you put it over the tape, the color sensor reads the red tape as having a red value of like 200, for example. What you could simply do is, for now I'm going to use a I'm gonna write it as copy over some of the motors. This is assuming I get a mecanum drive, although a tank drive is pretty much, actually it's essentially a tank drive because we don't need to strafe right now. I'm just gonna write it as if the robot is simply moving forwards. So you initialize the 4 motors same way you normally would with the DC motor. And then the color sensor is initialized in the hardware sensor, color sensor. And these are the names of the motors in the config. So once everything is initialized, once the op mode starts, you can easily just set all 4 of the motor powers to 1. And then you could have a simple while loop that just waits. So you might want to log some data in there so you can see the robot and what values it's reporting. So you would have simple color sensor dot red is, so the color sensor dot red value would tell us how much red the color sensor is seeing. So let's say you already tested this before using the simple telemetry dot add data logging mechanism, and you found that when it got over the tape, its red value went from 0 all the way up to like 200. You could have like a split threshold, maybe something like 100 or 150. You might have to calibrate that number, but essentially a value that will tell you once it detects that much red, or vice versa, when it isn't detecting that much red, just log the data. Don't do anything with the motors. Well, once we set the power to 1, just don't do anything. So this code will constantly run. All it'll do is it will tell the driver station how much red, green, and blue it is, but it isn't changing the power of the motor. So the robot is going to continue to move forward continuously. Then once you finally cross that threshold and end up having more than 150 red, I believe the red is on a scale of 0 to 255 because it's supposed to, most RGB elements are represented on that scale, where 0 represents a complete lack of that color, and the purest version of that color is considered to be the 255. So so a pure red tape would appear to be 255, while if no red is detected, if only another element is detected or no red is detected, the red amount is going to be 0. So you're using this code by having a simple while loop that essentially does nothing. It does log data in this case, so it's logging some data. But even without this, it would still work, because all you're doing is while the loop is while the color sensor is less than 150, you're just doing nothing. So the robot, because you already set the motor powers to 1.0, the robot is going to be continuously moving forward until it crosses that value. And then once it crosses that value, you want to set the motor powers to 0, and then that will cause the robot to stop once it reaches whatever red tape or red item on the ground you're looking for. And the code for a distance sensor is really similar to this. You would load it in this a very similar way, distance sensor. This one has a slightly different syntax, but you can use distance sensor and write the code like this and the proper name of whatever the device is called, so distance sensor or whatever it is named in the config, distance sensor. So by and the distance sensor is very similar. So instead, like instead of doing color sensor dot red, you might do or you could combine two cases. You could say distance sensor dot get distance. And there's a bunch of units here, including centimeter, inches, whichever one's most preferable you can use. So you could say that if it's really close to, for example, this says less than 20 inches. So that might be, for example, a wall. So if the robot is very close to a wall and it reads the red color, it goes, it has to be negated because we want to check if the distance is closer than 20. The other way around, sorry. What I was trying to say is we want this loop to keep running while the distance is greater than 20 inches away. So if it's greater than 20 inches away, you want to continue moving forward. Or if you haven't reached that red tape yet, you again want to continue moving forward. So only this code will only stop when both of these cases are false. So the distance sensor ends up somehow getting closer than 20 inches to a wall, and you end up on a red tape. So that might mean you're close to a red wall and you're on a red tape, for example. Then only would you set all your motor powers to 0 and just completely slow down. And there's a couple other sensors, but the most basic part is just you have to load it into the, you have to create a field for it first, because in an autonomous, you can get away with not creating a field. But in a teleop, you want to have the code for initializing separate from the code for looping. So you have to create a field so that you can access it from the multiple methods. You can access it from the init method, and you can access it from the run method. So here we access the init shooter from the init and from the loop. So you want to have it created as a field. In autonomous, you can do either. If you want to access it from other methods, if you create other methods to set motor powers, you would want to have it initialized as a field. So like a touch sensor, for example, it's very similar. You just create the field variable. You use the hardware map to get the touch sensor itself. And then depending on the sensor type, the method's going to vary. The distance sensor has get distance. The color sensor uses the red, green, blue, so color sensor dot red, green, or blue. And the touch sensor just has almost a single method called isPressed. It's very basic. So if I set this to not isPressed, what it's going to do is it's going to keep moving forward. And if you have the touch sensor on the right side, the correct side of the robot, once that touch sensor gets pushed, the robot will stop. So if you have it, so if the robot, for example, will ram against a wall, you could have it move forward until it touches the wall. Once it touches the wall, the touch sensor gets pressed, and then all 4 of the motors receive 0 power and then stop. So you can use the sensors to essentially allow your robot to see into the world and write code and logic that depends, so that your robot can run like independent of variables on the field. So even if the robot moves, it allows you to gain information into what's going on inside the field at that point. And then there's the gyro sensor. The gyro sensor is a little bit more complex because, and for all of these, there's usually examples that describe how to do it. So the gyro sensor is one. If you have a rev control hub or a rev expansion hub, there's a built-in IMU sensor. It's very powerful. It has some details about like how fast the robot is rotating, or an approximate integration to get like the velocity of the robot. But the most useful methods are the precise position, or the precise orientation of a robot, sorry. That will tell you like which way the robot is facing, and it allows you to do extremely precise turns on the robot because the internal gyro is very accurate. So you could have the robot spin exactly 90 degrees. So to write that, so in order to get that, you have to run, what is it? And there's a lot of like complex parameters that go into that. But there's a class itself called, this by the way is the brand name of Rev's internal IMU, the Bosch BNO055. You can set it to like degrees or radians. If you're using acceleration, you probably don't need this, but if you're trying to see how fast the robot is accelerating or how fast the robot is moving, you'd use the acceleration unit, which will tell you like how fast it's moving in meters per second squared. The calibration file isn't unnecessary. I think most of these aren't very useful. The most important one is the parameters.angle unit. So if you want to work in radians, by default it's set to radians, but it might be easier to just use degrees so that you don't have to do the radian conversions yourself. So this one, instead of being called something simple like touch sensor, is called BNOIMU. The IMU stands for integrated, I forgot. But it's essentially almost a synonym of gyro. And it's built into the Rev expansion hub or control hub. So if you have one of those, there's one built in. So this is the very basic code. So this doesn't even have to usually be set up in the robot config. By default, it's automatically expected that there's an IMU inside the robot called IMU. So you would get it similar to the other sensors. You just get it by doing hardware map.get. But unlike the other sensors, you do have to initialize the IMU. So here, since we want to convert it to degrees and we want the IMU to be properly ready, it takes a couple seconds. So you want to set the robot down and not move it, and in maybe 2 or 3 seconds it takes. You have to let it sit so that it can calibrate itself and be accurate and ready to go. So once you initialize it, to get the current robot's angle, you can do IMU.get angular orientation dot. So any three-dimensional object technically has 3 orientations, X, Y, Z. Depending on the way the Rev hub is mounted, what orientation you might have to use may vary. You can try all of them. There's 3 angles called first angle, second angle, third angle. If you like, for example, mount the rev hub flat, it might be first angle. But if it's attached to a wall of your robot and is facing sideways, it might be second angle. So you can use, you can just try out the 3 angles and figure out which one of the orientations the rev hub's in. And once you do that, you'll get an angular value. And because we set our angle units to degrees, it will tell you what degree your robot is facing at. It's going to start off at 0, right, when you initialize the robot. But as it turns, it's going to go up. So it will increase all the way to 360 degrees and wrap around back to 0. So a very simple example for might be if you look at if you want your robot to turn, what is it? If you want your robot to turn to the right, you'd have to set the left wheels to positive power, I believe, and the negative wheels to right, negative power. If you do that, what's going to happen is the robot will start turning clockwise because the left wheels are moving forwards and the right wheels are moving backwards. So the robot itself in place is turning clockwise. And then you can keep doing that until the gyro angle, that angular orientation dot, is less than 90, for example. So what this is going to do is the robot will keep rotating to the right slowly over time until it reaches 90 degrees. So this could be used as a method of making sure that the robot turns 90 degrees. So I could also like separate this into a method called turn, so that you can pass in, for example, how far you want the robot to turn. So let's say that one thing that you do have to account for is, let's say that the user asked the robot to turn 90 degrees. That's not how you spell degrees. Okay. So like if the user asks the robot to turn like 90 degrees, you can take the current angle even before the op mode starts. You want to take the current angle. So let's say that the robot thinks it's at 180 degrees. So the current angle is 180 degrees, for example. If the user says, I want to turn 90 degrees, then the target angle, the angle we should end up at, is 270. We take the current angle, and then we add whatever amount the user asked to turn. So that our target angle would be 270 degrees, because the robot's already at 180 in this scenario. And then you just say while the angle is less than the target angle, keep spinning. And you could use that to simply if you put this in front and then this after, you could simply use that method to turn a specific amount of degrees, turn 90 degrees, turn 180 degrees, or so forth. But the IMU is a little special compared to the other sensors because you have to initialize it, and you also have to wait after you run I believe the initialization method. It says it can take fairly long, possibly several tens of milliseconds. But when it's initializing, it's best to just let it sit and do its thing. So it might take like a second or longer than a regular op mode, but it's because it needs it to allow the robot to be accurate in reporting. So this code will allow you to, like, for example, turn the robot to any specific amount of degrees. And because the IMU, even though the IMU is like an internal aspect of the robot, it's very accurate, and it can be used to like turn to pretty much any. It tends to be accurate throughout the game. Some teams experience a little bit of drift, but most of the time, if you need to get your orientation at any point along the op mode, you can just use your gyro. So again, if you guys have any questions, feel free. Otherwise, I will dive into a little bit of TensorFlow and Vuforia, which again, so one of the main goals this year is during the autonomous period, the wobble goal needs to be placed in one of 3 locations, depending on how many rings there are on the field, whether it's 1 ring, 0 rings, 1 ring, or 4 ring. This picture here is from the previous year's game, but it represents a similar use of TensorFlow, so I'm presenting it. TensorFlow is a artificial intelligence model. It allows you to detect objects on the field, and it can be used for a variety of visual tasks. But in our FTC game, what happens is essentially the first team calibrates. I believe they just take a bunch of pictures of various rings in various positions, and they create their own model that for detecting rings. So it's essentially they would take a bunch of pictures of rings and then manually draw out where in the picture each ring is. And then the artificial intelligence learns to pick that up and identify, oh, that's a ring over there. And it will learn to automatically draw boundaries itself. So TensorFlow is used for visual tasks. In this case, it can be used to identify rings spread out through the field, and also identify like how many rings are in the ring stack. And then there's Vuforia, which this year there's multiple VU marks, of course. Like I know, for example, there's 2 Vuforia VU marks right under the shooters. These are little pictures that they put right around the field. And wherever the pictures are, you can, Vuforia is a powerful library. So essentially, as long as your robot is facing a picture, it can tell you exactly where on the field you are based on that picture. So it calculates the distance to that picture, what angle the picture is at, how far away it is, whether it appears small or large, and then use some mechanisms to identify how far away that VU mark is. And based on that, and where it expects that VU mark to be, it can then backwards calculate its own position on the field. You can look inside the sample op modes again. I recommend looking there, and you'll find some code explaining like how the TensorFlow mechanism, like the code to use to run it. Here, the very first line here is referring to it's called a monitor ID. If you have an FTC, if you're using an FTC robot controller phone, it doesn't help much on the control hub, but if you're using the FTC robot controller phone, you can get a visual preview of what's going on the webcam by I think I forgot to copy the documentation. Okay. And I forgot to mention, you can also combine Vuforia and TensorFlow. So you can use Vuforia to detect your location on the field, and then you can use TensorFlow to detect the ring stacks. And the example op modes also show that the Vuforia and TensorFlow tend to be linked. So you can use both of them at the same time. Then maybe I should start with Vuforia because it seems to depend. I'll skip over the Vuforia part and get back to it. But essentially this TensorFlow code is the first part, again, gets the specific, it's a part of the Android SDK where you're trying to identify a specific view on the robot controller. So it grabs the specific ID of the monitor on the robot controller so it can display the webcam. These parameters, there's a lot of adjustments that can be done. The most important one is the min result confidence. Every time TensorFlow detects a ring, there's a certain confidence it applies to it. So it says like, I'm 60% confident this is a ring. So if here it's been set to 0.8, so that means that it will only tell you that it found a ring if it's at least 80% certain that that ring is an actual ring. There's a couple others, but most of them are from a technical standpoint. The most important one is the minimum result confidence. So if you're seeing like rings get accidentally mistaken, you might want to like fine tune that. So if you set it higher, it will only report rings that it absolutely is certain are rings, but you might miss other rings. So depending on the rate of false positives and false negatives you're getting, you should fine tune that. And then this mechanism here links it to Vuforia. So you pass in these parameters of what you want, and then you also have to combine the Vuforia element, and I'll explain how to initialize the Vuforia as well. And then using a combination of both of them, you can get TensorFlow. And this final code is loading the models. TensorFlow by itself is just an artificial intelligence library. It can do like thousands of different things depending on what you give it. So here we are passing in the elements. This is a file, ultimategoal.tfl lite is a file created by First. You don't have to worry like too much about it, but it's essentially the asset that First has created that allows you to detect rings. It's very specific to this year. There's multiple assets in there. There's a skystone asset if you're trying to detect skystones, and other ones from previous years. But this year's is called ultimate goal, and you have to pass in these two strings as well for the label first element and label second element. But using those variables and values, TensorFlow can tell you where each one of the rings are. And then once it is initialized like that, you can then do run a loop constantly. And the op mode is active here is necessary because you don't want to set it to while true. If you do that, when you try to stop the op mode from the robot controller, the loop will continue to keep on going forever, and it will just eventually crash. But while op mode is active, we'll keep the loop going only while the user hasn't pressed the stop button on the driver station. So first you want to initialize TensorFlow, and you want to do that before the op mode starts, because initializing TensorFlow does take some time, and you do not want to waste the actual autonomous time after the robot is supposed to be running to initialize it. So you want to do all of that before the op mode starts. You wait for start, and then while the op mode is active, TensorFlow has multiple methods: activate, deactivate for the actual system. And then there's get updated recognitions. There's get recognitions, which will give you a list of every single ring it detects. get updated recognitions will present any, a recognition is essentially a ring. So you can look at each recognition, which is essentially, this year it's a ring, and then it'll give you a bunch of details about that ring that it found. You have get confidence, which will give you a value between 0 and 1 for how confident it is that that item that it sees there is actually a ring. And you can see, because we have a minimum confidence of 0.8, it will only present us rings that it thinks is 80% certain it's an actual ring. You have, like, for example, gets bottom, get top, get height. These are all like coordinates of where the exact ring is. So you could use, for example, get top to see how high up the ring is. And if you, an example method of how you might try to decipher how many rings there are is you would use this get top method to look through every single ring and find where the height of that ring is. And using that, you can decipher, for example, if it doesn't find any rings at all, then likely there, if what is it, if tfod.get recognitions, if the length of this is completely 0, then that just might mean that there's no rings at all on the field, and that there are no rings over here, which means it goes to the, I was saying, if there are no rings at all, you have to move to the first wobble goal placement. If there is one ring, you'd want to go here. And if there's 3 rings, you'd want to go to the very back side, the one close to the goal. So you could just also just simply check the amount of rings the TensorFlow detects. So if there are 0 rings, then you know that there is time to go to the first wobble goal location. If there's 1 ring, you could go to the other one, the middle one. And if it's 4, you go to the back one. Or you could also check the height of each ring and see how high the ring stack is, and check if that height of the ring stack would match a 1 ring scenario or a 4 ring scenario. And then initializing Vuforia, there's like a bunch of parameters, and you should probably read through these instructions. It's inside, again, the external samples called concept Vuforia navigation. You have to go to Vuforia's website and download a license key and paste it in here. And then the rest of the code is explains how to link it up to, again, to the camera on the FTC robot controller, so you can get a preview. And then there's also Vuforia parameters themselves, such as like which way the camera direction is, and various aspects. Like if you have, like, if you wanted to calibrate the webcam, you could plug in a file that will like stretch or modify the size of the webcam, or if it has any distortions, it will help adjust for that. Once you create your actual Vuforia object, you can yeah, this code, it goes through like a lot of detail, like where each one of the targets is on the field. You have to add it into the code and mark its location, its translation. So you're essentially, you have to go through the code of like marking every single object on the field and where it is, so that the once as you're traveling around, for like the FTC robot controller will internally have a bunch of pictures of all the VU marks you're going to see on the field. So here you can see an example VU mark down here. And the FTC robot controller will have its own version of that picture on its inside the FTC robot controller, and then it'll try to match them up. But once all that code is set up, the main the main code exists in a list of trackables. So if I can find at least like one of them. Each one of the little pictures on the field is called a trackable. So you can do, you can give each trackable a name, and then inside there, you can have get location, which will return the location of the trackable itself, but you can also, where is it? You can also use that to get the location of the robot itself based on each trackable. So the code, you can just copy and like paste the Vuforia code given there. But once you copy it, it'll create a field called robot location. And then inside there, essentially, there is the robot's position. So you can access where exactly on the field the robot itself is. X and Y position, X, Y, and Z technically. So you can get a very precise location of where the robot is, and it will constantly update every single time it sees an image. So you can use a sort of use that sort of mechanism to see. So you could like creatively position your robot so that as it does its autonomous, it ends up looking at each image. Then you can, as long as you ensure that it's trying to look at an image, you can usually get a pretty accurate target and be able to accurately identify where the robot is based on how far away that image is. So it's very useful for positioning based on those external images. And then again, this can be combined with TensorFlow, so you can combine the TensorFlow and Vuforia aspects, and that will allow you to use both of those mechanisms at the same time. This year, I believe there are 6 VUMarks, one on each one of the power shots. This is a remote field setup, so there's only 3. On the main competition field, I think there's 6. So one example could be, for example, you could look at this VUMark right here in front of the in front of the goal, and based on where that is, you could position yourself in line for the power shot. One of the years I remember we had a simple, I believe like previous years, we had simple code on a while loop. So it said while the robot's distance from that VUMark is less than this. But it's very powerful because it not only tells you how far away that image is, but it can also tell an accurate, pretty accurate estimate of where the robot is on the field. The only disadvantage might be that it takes like a second or two to accurately predict where your location is, which is why I believe Rohan and Isha later today will go into a little bit of introduction or explanation of odometry and Roadrunner, which would allow you to use like odometry or motor encoders to figure out your position on the field. So it's an alternate, using odometry is like an alternate localization method, Vuforia is while Vuforia works on your webcam and identifying where each VuMark is and how far away you are based on that webcam, odometry works by like having little wheels on the bottom that track your position continuously. So it has a much faster update rate, but it's more mechanically complex than just throwing on a webcam, and it is a little bit more difficult to get very accurate. While the VuMarks, you can pretty much copy and paste the code, and it will accurately tell you the position of the navigation images and your current location. One thing I also wanted to show is an elapsed timer. Um, it's part of the FTC repositories. So FTC has an inbuilt mechanism called an elapsed timer. This allows you to like just calculate how long it's been and measure time in a pretty simple and easy mechanism. So like while the inbuilt Java methods tend to be specific to like milliseconds or be limited to like integers, the elapsed timer allows you to access like any units, so you can like access milliseconds, nanoseconds, and stuff like that. What you would do is essentially you could like, let's say for example we want the shooter motor to run for like exactly 2 seconds. We could set so we would initialize it the same way, hardware map. So we could get the shooter motor, and then to set the actual power, we could set the power to full speed. And then if we want to run, for example, exactly 2 seconds, we can do timer.reset. And then while timer.seconds is less than 0.5. If we wanted to run for 2 seconds, we could do 2.0 or just 2. And then that will let that will allow the shooter to continue running while this code will let the shooter run for exactly 2 seconds and then stop. So you have to call timer.reset because the timer internally is continuously counting. So you have to reset it when you're about to use it. And then you can have a simple, like here, a simple while loop that will measure how long that will make sure that your shooter is on for exactly 2 seconds before stopping. So you can see here an example autonomous where this is a simple tank drive. So they're trying to drive forward for 3 seconds. So they set both the left drive and the right drive to full speed or for whatever forward power is. And then while the name of the timer they have is called runtime. So while it's less than 3 seconds, the robot is moving forward. They also changed on op mode is active. This is because if the user presses stop while the timer is running, this will become false and the while loop will immediately exit so that you're not stuck continuously moving forward. If the op mode is supposed to end, it will immediately end. So to spin to the right, they have the left motors moving forwards and the right motors moving backwards, which will cause the robot to spin right or clockwise. And again, 1.3 seconds. So they just, every time they're about to use the timer, they just simply reset the timer set it, and then measure how many seconds it's been since they reset the timer. And here they do it again with 1 second. And when the op mode is about to end, they just shut down the, this is a tank drive, so there's only 2 motors to stop. And then they have a claw mechanism that they also disable. And in a regular op mode, you can use a sleep method to just have the robot sleep a second or two. In a teleop, you cannot sleep inside the loop method because otherwise the program will freeze. So inside a loop method, you cannot sleep. But inside a regular run op mode method, you can, if you wanted to, just simply also use the sleep method here and just sleep 2000 milliseconds. Instead of having to do a timer, it's an alternative method, but the timer is also very useful because it lets you access stuff in seconds and use normal units. If you have any questions, you can ask. Otherwise, at 11:30, we are going to take a short, like 30-minute break. And at 12, we're going to start have our odometry and introduction to Roadrunner presentation. And then we're planning on having an open discussion at 1 o'clock.